Hi again, everybody. Welcome back. We've been talking about angular momentum. Momentum being the sign or the symbol L, and it is a vector quantity. And we're going to do an example in just a second right here. But one thing I want to point out is that just like linear momentum can be positive or negative, so can angular momentum. If you're do you remember how we talked about how your angular momentum is really your linear momentum times some radius, right? Times some radius from the center of, say, a merry-go-round or something like that, times the sine of the angle between them, the linear momentum and the radius. Well, if that angle is changing, as you approach something at a varying angle, as that angle increases up to 90, your momentum is going to be increasing, all right? And therefore, you're going to have a positive rotation or angular speed when as you're kind of passing that pivot point. But you're going to have a negative momentum as your angle is decreasing. So you're approaching something at a differing angle. Right? As that angle gets less and less and less, that means your linear momentum gets less and less as well. So we just need to account for the angle at any one point that an object is approaching a rotating object. Like I said, kind of like a person running towards a merry-go-round. And the ideal angle that would give you the maximum momentum would be 90 degrees. And so we use that. We use the moment arm to kind of account for that. All right, let's see if we can make some sense of this by applying it to an example. It's going to be example 1113. I think our numbering system got messed up a little bit in the background, but we're just going to, or in the past, but we're going to just go with 13 right now. All right, there are three parts to this. A, B, and C, but all of these are directly related to what we've just been talking about, okay? So we've got a child running with a speed of 4.10 meters per second. All right, let's write down that. Velocity. That's not a good color to use. It's a little too light. Velocity, let's go with blue. Velocity equals 4.10 meters per second. A 21.2 kilogram child, so mass of the child equals 21.2 kilograms, is heading towards the rim of a merry-go-round. The radius of the merry-go-round, radius is 2.00 meters, and the child moves in the direction indicated in the picture below. Clearly, this child has not taken physics yet and doesn't realize that if they're running towards the edge of the merry-go-round, the best angle to approach the edge would be tangentially. Well, this person is not approaching the angle, or approaching the edge of the merry-go-round tangentially. They're hitting it not quite straight on. That would be very stupid, but at a 45-degree angle, or you might say, or a 135-degree angle, if this is your velocity, and that's your radius right there. Either way, the sine of 135 and the sine of 45 is going to be the same thing, so we need to take that into account when finding their actual angular momentum. All right, we're finding it. Part A is L. See, with respect to, I don't know, some axis of rotation. We'll do that right there. So what's the angular momentum with respect of the child with respect to the axis of rotation? Part B, we're being asked to find what is a moment arm. So R perpendicular right there is a moment arm. And part C, we're being asked to find what is the angular momentum. Well, it's the same thing really as this right here, but we're going to find it a little bit differently just to confirm that you can find it a couple of different ways. So L equals moment arm times mass times velocity. Okay? All right. And in fact, actually, before we start this real quick, the more I look at this, the more I realize that this is asking us exactly the same thing, A and C. Tell you what, let's just skip A and just go right to B and C. I'm trying to figure out how that would be different right there, but let's maybe it's just asking if it's going to be if the child's momentum is positive or negative. All right. Well, it's becoming. Anyway, let's just skip A and just go right from B to C. Okay, because I think A and C are going to be asking the same thing. Well, like you probably guessed, I'm going to have to shrink this thing down a little bit. All right. And part B, we're going to be asked to find the moment arm. All right. Remember, the moment arm is the right angle radius. Even if their approach to the edge of the merry-go-round isn't exactly 90 degrees, there is some sort of a hypothetical right angle radius in there somewhere, and we can figure that out by taking the sine of theta. So the moment arm is what? Well, that's going to be the radius times the sine of, let's see, well, it's going to be 135 degrees, really. 135 right there, all right? So the radius is 2.00 meters times the sine of 135. What do we get if we calculate that out? We get 1.41. All right, so the moment arm is 1.41 meters, and it wouldn't be at the edge. It would be kind of like, I don't know, with respect to the child, it would be somewhere right in here. So if they were actually able to kind of maybe jump over the edge and land on the merry-go-round right there at that point, partway between the center and the edge, they would be applying a right angle momentum to it, and so their momentum would be calculated from this point, not from the edge right there. So if you run at the edge at any angle other than tangentially, or an angle other than 90 degrees to the radius, then it's going to be some other moment arm, some sort of other hypothetical moment arm. In this case, it would be right there, and that would be 1.41 meters from the center. Again, I'm still trying to figure out how part A and C would be different. I was going to solve part A the same way I'm going to solve part C, but we're going to do that right now anyway. All right, so part C, we want to find what is the angular momentum. Well, we can say that it's L equals radius times momentum times the sine of the angle between them, or we can say that L equals the moment arm radius. So we've already accounted for that sine, sine of theta. So that's in there already, to sine 135, times linear momentum, which of course we know is mass times velocity. And that's really what part C is asking us for right there. All right. So the moment arm is 1.41 meters. The velocity should be a vector. The mass of the child is 21.2 kilograms. And the velocity of the child is 4.10 meters per second. Multiplying that all together will give us the angular momentum that that child has with respect to the center of the merry-go-round. 1.41 times 21.2 times 4.10. I get 122. Actually, nope, 123. And what are the units for that going to be, by the way? Well, it's going to be, it's our radius, which is in meters, mass, which is in kilograms, and then velocity, which is in meters per second. So it's going to be meters, it's going to be kilogram meters squared per second, right? Kilogram meters squared per second. You'll recall that linear velocity would be kilogram meters per second. That's mass times velocity. But since we have this multiplied by the radius r, there's going to be another mass in there. So, I'm sorry, another length, another distance, another meters. So L is going to be kilogram meters squared per second. Other than that, they're basically analogous to each other. This is just the rotational analog to linear momentum. All right. Example 11.3, a good application of linear momentum with regards to rotating objects and turning it into rotational momentum. That's it for this problem. Thanks for following along, and I'll see you on the next one.